the end of the last video, we talked about steps for determining an empirical formula. If I give you percentages, there are 4 steps that we're going to be looking at. We assume that we have 100 grams and convert percentages to grams. Then we take those grams and divide by the molar mass to get moles. And then we divide by the smallest moles to get an empirical formula. So let's start off by doing these steps again for another example. A compound is analyzed and found to contain 40% carbon, 7% hydrogen, and 53% oxygen. So it's a whole other compound, and there's 3 elements in that compound. What is the empirical formula? So let's do step 1. 40% carbon means I have 40 grams carbon. 7% hydrogen means I have 7 grams hydrogen. And then 53% oxygen will mean I have 53 grams oxygen. Okay, cool. Then step 2, convert those grams to moles. Well, the molar mass of carbon is about 12 grams per mole. The molar mass of hydrogen is about 1 gram per mole. And the molar mass of oxygen is about 16 grams per mole. So grams divided by molar mass is going to give me moles. So 40 grams of that carbon divided by 12 grams, divided by 12, and I get 3.333 repeating moles of carbon in this compound. And then I have 7 grams of hydrogen divided by the 1 gram per mole. Let's just say gram per mole for fun, of hydrogen, and I get 7 moles of hydrogen. Cool. And then I'll do oxygen. 53 grams of oxygen divided by about 16 grams per mole of oxygen, and 53 divided by 16 is 3.3, also approximately 3.31 moles of oxygen. And then the third step says take these moles, divide by the smallest moles. Well, between the 3 of them, it looks like 3.31 or 3.3 is the smallest. So I'm going to take all 3 of these. I'm going to do carbon first. I do 3.33 divided by 3.31, and we get about 1 carbon. Then we'll do 7 divided by 3.31, and we get about 2.11, so we could say about 2 hydrogen. And then, of course, 3, and this is for hydrogen. And then, of course, for oxygen, we could do 3.31 divided by 3.31, and we get about 1 oxygen. So I have 1 carbon, 2 hydrogens, 1 oxygen in this formula. And now round each to the nearest whole number, which is what we did, and then write as subscripts. So how can I write a chemical formula that has 1 carbon, 2 hydrogens, 1 oxygen? Well, I'll get C1H2O1, which is just CH2O. Done. This is the empirical formula. I will not go any further. Now, sometimes the rounding is not so great. I have to round to the nearest whole number, or maybe I cannot round to the nearest whole number, and I have to find a better ratio. If I ever get a decimal of 0.3, that's telling me that I have some sort of 1 to 3 ratio going on. If I ever get a ratio of 1.33 ending there, that means I have like a 4 to 3 ratio. If I get a ratio of 2.5 or a decimal of 2.5, I must have a 5 to 2 mole ratio. So for example, if we found a compound containing only N and O to have 0.8 moles of N and 1.25 moles of O, let's skipping to step 3. Let's divide by the smallest moles of 1.2. So let's say I was doing N, I would get 0.8 mole of N divided by, oh, whoops, I'm doing this wrong. Let's just get the mole ratio here. I have 0.8 mole of N divided by 1.2 mole of O. And right now, 0.8 divided by 1.2 is 0.6667 moles of N to every 1 mole of O. 0.666 is giving me a 2 to 3 ratio. So really, if I had 0.66 N to O, what I really have is 2 moles of N for every 3 moles of O. Let's do this using step 3, actually. If I was doing step 3, I would divide both by the smallest moles. So if I had N, I would have 0.8 divided by 0.8, which is 1 N. And then if I had O, I would have 1.2 divided by 0.8. And that 1.2 divided by 0.8 is 1.5. So if I get a 1.5 ratio, or if I'm getting a 1.50 to 1N, right? I did that upside down. That means I must have 3 moles of O to every 2 moles of N. Look, they both show me the same thing. That means our ratio of N to O is actually 3O for every 2N. And if I want to write a formula, it would be N2O3. So I just wanted you to be careful that sometimes the rounding isn't so great. If you do end up getting something that I cannot or don't round to 1, maybe it's not quite 0.9 or 0.8 or 1.1, maybe I get somewhere in the middle, you could use these decimals and fractions to help you with that. This, you may or may not see these on future quizzes, but I wanted to show that to you here. This next example is that of using improper fractions for the ratio. I'm going to leave this here for as like extra credit, if you so will. It's not going to be required, okay? So I have 2 problems here that are going to be a bit of extra credit if you wanted. You could show the work here, turn that in, help raise some missing assignments or low points here. But it will not be required, but I still wanted to show it to you. So just a quick recap. If you see any of these decimals when you divide, specifically 1.33, 1.5, 2, 2.5, 3.0, you're really dealing with improper fractions or fractions like this, where instead of it being, like we just did, instead of it being 1.5, it's really a 3 to 2 ratio. Or we did 0.66, it's really a 2 to 3 ratio. That's upside down. All right, so I'm going to end this little video here. Just more examples of determining empirical formula. We did another example, and I showed you an example of what would happen if we don't have whole numbers here. In our last video, we'll be talking about and putting it together with molecular formulas and determining them from empirical formulas.